embraced it. But fire can become the enemy.
Whoa! A spark can start a raging inferno.
This is insane.
Just like something out of a movie.
But where there's smoke, there's science.
There are lessons in the ashes.
So researchers are heading straight into the fire.
So you really only have a small window to get out of your house.
Can ancient wisdom
We are the boss of the fire.
and cutting-edge technology spark new ways to face the flames? Mike Flanagan has seen more forests in flames than he can count.
We've just started the fire season. We have hundreds of fires going.
But in the summer of 2017, as he heads into the Canadian province of British Columbia, even this veteran wildfire scientist is in awe.
This is an incredible fire. It's a rare beast. So we're just north of Ashcroft, and behind me you can see a very aggressive wildfire spreading up that hill. Well, just look at the amount of smoke. And if you watch it for a while, you can see how quickly it's moving. And at times we can see large flames.
It's mid-July, early in the fire season. But already, British Columbia is burning.
Go way to the left. Can we get through there?
By the end of the summer, more than 1 million hectares go up in flames.
Time to leave.
Thousands of residents are evacuated. More than 4,700 personnel battle intense infernos.
The reason why this is happening with climate change, the warmer it gets, the more fire we see. Whoa, you see that's, in the last few minutes, this has grown tremendously.
To the ancient Greeks, it was one of the 4 elements of the universe, a force of nature stolen from the gods and given to mankind. But fire isn't a substance, it's a process. When fuel comes into contact with air and is heated to the point of ignition, it creates a chemical reaction.
I love fire. I'm like a moth drawn to the flame. It all started at my first birthday. So I had a cake and had 1 candle, of course, and I was drawn to the flame. I stuck my finger in the flame and I started to cry, but I kept my finger in there. Ever since then, I've been fascinated by fire.
He was one of the first scientists to study how our changing climate changes fire.
The warmer we get, the more fire we have. The more fire we have, the more greenhouse gases that are released. The more greenhouse gases released, the warmer we get. A vicious cycle. There is a recipe for fires to occur. You need 3 ingredients. The first is the fuel, the stuff that burns. How much you have, how dry it is, really important. Second, you need an ignition agent, people or lightning. Third, you need weather conducive to fire. Hot, dry, windy weather like we see right now.
Those trees on the mountain, those are fuel. And so are the valleys. Powder kegs of sage, brush, and grass.
The fuels here are so dry. When you walk on the grass, it crunches.
Before he became a world-renowned fire researcher, Flanagan was a meteorologist. He understands the crucial link between fire and weather.
Sometimes fire can be counterintuitive. There was a very wet winter in British Columbia, followed by flooding in the spring. And some people would think, well, given all that moisture, we won't have a fire problem. But a wet winter may actually make the fire problem worse in the summer because it creates more grass. And then in the summer, it dies, and that becomes fuel for the fire. There's more fuel, very flammable, burns quickly, so the fire is more intense and harder to control.
If you're talking about fire behavior, I would say there are many mysteries left. We really don't understand how fire spreads.
Mark Finney used to put fires out. Now at the Missoula Fire Sciences Lab in Montana, he's lighting them.
Are you ready? Okay, then let's go. In the laboratory here, what we've got is a large tilting platform. These fuels that we create are made out of laser-cut cardboard.
In this specialized burn chamber, they're simulating a spreading wildfire to solve a fundamental puzzle.
Everybody knows that heat rises. So if heat rises, how is it that fires can spread horizontally? That heat should go straight up, just like a hot air balloon rising up into the sky. So how is the heat from the fire being transferred to the new fuel particles that haven't ignited yet? That's never been understood.
Until now. With the help of high-speed cameras that can zero in on the flame structure itself.
So what we're seeing is this very regular pattern of peaks and troughs. So you see these U-shaped depressions that open up and then they close up again. When flames go up, something has to come down in order to replace it. The cold air that's coming down to replace the rising hot flames is pushing the flames down into the fuel. And it splays it out. It pushes it out in all directions. And it pushes the flames forward. So this has gone a long ways to answering one of the questions that we've been after for so long. Once we've recognized this pattern, we see it everywhere. We see it in fires big and small.
By examining flame structure on a small scale, Finney hopes he can help fire crews anticipate how a blaze will behave.
The video from real fires shows exactly the same features, and what you see is the fire is moving around, there's a lot of chaos, a lot of people would describe it as random, but it's not actually random. There's very good explanations for what the flames are doing and why they're doing it.
Flames are the visible glow of hot gases. And they're spreading rapidly, just down the highway from Finney's lab. Montana is experiencing one of the most severe fire seasons in decades. Just like British Columbia, where Mother Nature is demonstrating her power.
Fire can create its own weather. It creates winds. Just think of a fireplace, and you get a good fire going, you can feel the draft. Multiply that by 10,000 times, and this is what that fire is doing. It's sucking air and oxygen to feed that fire.
Nature even creates a fire whirl that resembles a flaming tornado. They recreate it in the lab by fanning the flames from opposite directions.
The air is flowing in a counter-rotating kind of way. So one is coming in this way and the other intake is that way, and that causes it to start to spin. It's exactly like an ice skater, where they bring their arms and legs in, they start spinning faster, and that's exactly what's happening here.
But fire also generates a far more common phenomenon: thunderstorms.
It builds a cloud, a convection column, that can generate lightning. Many H-bombs worth of energy are being released right now by this firestorm.
Lightning strikes Canada about 2 million times a year. And climate change scientists have issued a stark warning. A 1-degree rise in temperature leads to a 12% increase in lightning.
In British Columbia, 60% of the wildfires are started by lightning, and some of these are from what we call dry lightning. That's where you get the lightning from the thunderstorm, but the rain does not reach the ground. Lightning hits a tree, travels down the trunk to the base of the tree into a bed of dry needles. It starts a fire, and it can smolder there for days or even weeks. And then you get hot, dry, windy weather, and it flares up, and you have a wildfire.
Back in Montana, the pine forests continue to burn. And Sarah McAllister wants to know why, especially when fuels like these needles are alive.
So one of the great mysteries we have in wildland fire right now is how something like this burns. They're basically full of water, which is something that logically doesn't burn, right? So everything we know about how things ignite and burn is completely like thrown out the window with something with a live fuel like this. One of the things that we think is going on is that it's living, it's breathing, it's got water stored in the cells. So when you heat it up, they'll actually pop like popcorn. There's a lot of explosive ejection of vapor that comes out of it. And we think that it's bringing a lot of flammable stuff with it, like the cell contents, the sugars and starches, and everything else that's stored within the live fuel itself. I did not grow up playing with fire. I was a child of the Smokey Bear era. Fire was bad. In fact, my mom really actually doesn't understand my research because I was never that kid who was lighting things on fire all the time.
The poster bear for fire prevention equated fire with danger. One of the reasons wildfire, an essential part of the ecosystem, has become the enemy.
The fact is our natural reaction is to try to protect ourselves from fire, but by putting fires out in fire-dependent ecosystems, what we do is we disrupt the entire cycle. So essentially it's natural selection for only the most extreme fires, and that is the fire paradox, where the harder we try to remove fire from a fire-dependent ecosystem, the worse it gets when it does happen.
This is a very high-intensity fire spreading rapidly.
The biggest fire in British Columbia is still growing and could double overnight to more than 1,000 times the size of New York's Central Park.
As the wind dies down tonight, this fire will go to sleep. Tomorrow, we expect stronger winds. Look out.
Oh, you can feel the heat. Zoomed in. Holy shit.
It's only been a year since the last major disaster singed the Canadian psyche. The 2016 fire in Fort McMurray, Alberta, is the one they call the Beast. Not just because of its size, but because of its enormous appetite, devouring so much in its path.
Fire is opportunistic, and it is greedy. It's always looking for more fuel. So it's probing, looking for a wick, looking for a pathway. It takes no prisoner.
So this is all part of Fort McMurray, and here's a forest adjacent to structures. And this is a very intense fire that went through. You can still see the charred boles of the trees.
Now, after one of the most catastrophic fires in Canadian history, Mike Flanagan is sounding the alarm.
The Fort McMurray fire is a wake-up call. It was almost unthinkable that you would evacuate a city of almost 90,000 people. But where fire intersects with people, you have disastrous results.
It's called the wildland-urban interface. People living on the edge of a forest, shrubland, or grassland, and living with the risk of wildfire. In Canada, that adds up to 32 million hectares. 60% of Canadian communities face a potential threat.
We're living out in the woods now more than ever because people love to be in the woods. But with that comes the risk of wildland fire. What can we do? We may not be able to eliminate all the risk, but we can do things to reduce the risk.
That's why Alan Westhaver has come to town. As a kind of fire detective, he's had a front row seat to this disaster story.
I'm sitting on a park bench at the very edge of Fort McMurray that was exposed to all the heat, flames of the wildfire, yet it didn't ignite.
Across the street, a once vibrant neighborhood that was set ablaze is now a patchwork of empty lots.
It would appear that this bench being here, that was a miracle.
No miracle. For Westhaver, it's just science. Fires don't necessarily ignite just because hot flames are nearby.
There are a lot of myths about how homes catch fire. And one of the things that really catches our eye are the large, giant flames. A tsunami or a lava flow that just engulfs everything in its path and nothing could be done. But it's not the big flames that are necessarily the problem.
You can feel the heat.
Michelle Chamberlain was sleeping off a shift in the oil fields when he got an urgent call to evacuate his hometown.
You could really feel the pressure to try and get out of here, and things started getting a little more surreal. It was like something out of a movie.
It was a movie, in fact, or at least a video captured by dash cams at the front and rear of Michelle's truck.
Now you can really see the sky is darkening and flames are starting to show up. Looks like this motorcycle is just getting a little uncomfortable with the heat. How did it feel to you?
It felt like an oven, like when you open an oven, all that heat just rushes right out.
When Alan Westhaver discovered Michelle's footage on YouTube, it unlocked the clue to a fiery mystery.
Michelle's video really provides the best graphic example of how homes ignite when the fire is moving from the forest and approaching urban areas. Some of those flames at times are reaching 15 or 20 meters above the fire, and the wind is pushing them towards the homes, but never across the road. There was a virtual blizzard of embers coming from the fire, bouncing off the pavement, pelting off the front windows of Michelle's vehicle.
Embers, small firebrands of burning bark, cones, and branches.
Some of them are flaming, some of them are just glowing, smoldering.
Sailing on the wind, landing in bone-dry front yards, and wreaking havoc.
Right here, we can see that the first group of ember ignitions on the house side of the street. And we can see a small slot fire igniting here in a flower bed. Watch as those flames start to quickly grow. The wind is tilting them towards and into contact with the wooden deck in front of the house. So the take-home lesson really is that it's not the giant flames that are swallowing homes and igniting them. It's those tiny raisin-sized embers that are falling by the thousands, by the millions. What we really need to do is think like an ember and break up those little pathways that fire could move along and reduce the vulnerability of our home.
Westaver was hired by the Institute of Catastrophic Loss Reduction to investigate some of the 2,400 structures destroyed in the fire.
Everything that I needed to see to do my research was visible on the ground.
When he first came to Fort McMurray, the ground was still smoldering.
The city was virtually empty of its citizens. It felt like I was walking on sacred ground.
He closely examined 98 properties to determine why one house goes up in flames while the one next door survives.
There are lessons in the ashes. You know, the answers mostly lie in our own backyards. I searched for locations where side by side one home was standing and its neighbor had been burned. And I compared them to the hazard factors that we know make homes vulnerable.
So what do we have here?
This is a great example, Mike, of one of the places where you can really see why some homes survived and others didn't. Because this home in particular was very resistant to fire ignition.
Now, Westaver is on a mission to educate the public and other scientists.
The owner was very careful how he managed the property, starting from the top to the bottom, a non-combustible roof, siding that's resistant to ignition. The lawn was watered. Combustible objects like the firewood pile, the tool shed, all the other materials were placed far away from the home so that they wouldn't carry the fire towards it.
I noticed that there's a good separation between the forest and the homes. There's almost 10 meters here of grass. And it looks like half the street burned down and half of it didn't.
I think one of the big myths about wildfire is that we're helpless victims. I found that the ignition of homes is anything but random. It depends on the hazard factors that are there. Most of the fire smart measures that we need to apply around our homes are tasks that we would putter away at on a Saturday afternoon or an evening after work.
We were told our house was gone, and it wasn't until we saw a helicopter fly over on the news that we saw it was still standing.
A small weakness that we do notice is the wooden fence is attached directly to the house.
Yes.
So a fence can be that conduit for fire to move between many homes.
Right.
So the answer to that is fairly simple, is putting in probably a metal post against the house so that there's some separation.
Okay.
Would be beneficial. Then you'd be 100%.
We're getting there. I think we've learned a lot of things from this fire.
So this home was lost, and obviously that home, and
The whole row and
the whole
then
row.
across the
Yeah.
street.
This house was damaged, but certain choices, using stucco, planting vegetation away from the house, may have saved it.
Your choice of shrubbery inside that planter is a deciduous broadleaf plant that generally holds on to a lot more water, and it's not going to burn like a juniper or an ornamental cedar or, something like that. In my experience, the worst culprits when it comes to vegetation are these ornamental junipers and cedars. When I look at those, I see a can of gasoline.
Gasoline, because these evergreens are highly flammable. But wildfire risk is about more than what we plant in the yard or how we design our homes. It's about where we build them in the first place.
Impactful fires are almost like real estate. Location, location, location.
Here in Fort McMurray, entire neighborhoods sit up above the curving rivers and scenic valleys. So it's an uphill battle if you're fighting a fire.
Fires race up a slope, and if a community is right beside the slope, as in this case in the western side of Fort McMurray, the fire races right into town.
Fires can spread uphill much faster than they could on flat ground. And so what I'm trying to do is understand why that's happening.
At the Missoula Fire Sciences Lab, researcher Torben Grumstrup is simulating a spreading wildfire.
So what we see in this experiment is the visible flames, but there's a whole nother world that are invisible to our eyes. What we can't see here is the hot air produced by the flames rising up into the air.
Using a special technique called shadowgraphing, he can look inside the flames.
You can see in the shadowgraph that the hot gases rise straight up into the air. No surprises there. But if we raise the slope of the table, the behavior changes significantly. Instead of the hot gases rising directly into the air, they actually ride along the surface of the table before rising up. In a real wildfire, with the flow of hot combustion gases riding up the hill, these combustion gases heat up the fuel that's ahead of the fire, the unburned fuel that the fire hasn't gotten to yet, and because of that, the fire will spread up the hill much faster. So the reason this research is important is because there are times when firefighters have to work uphill from a fire. That's just the fact of the matter. And so what we're learning here can be translated into tactical decisions on the ground.
Forest fires are so hot, about 1,000 degrees Celsius, they actually burn the bark off the tree.
A graveyard of blackened aspen trees, not even the most flammable, like conifers, now surrounds the city. So how do we slow the spread of devastating wildfires? There are proven, though costly, measures, eliminating or thinning some trees, for example, or even closing off some forests altogether. It all depends if we're willing to pay the price.
We want to have our cake and eat it too, but the reality is we have to learn to live with fire, to coexist with fire, because we expect more fires, we expect more intense fires, so we have to do something about it. It's not just Fort McMurray. Almost any community in the boreal forest is at risk, and with climate change, that risk is increasing. It really is true. A spark can start a raging inferno.
But infernos don't just blaze through the forest. Some of the deadliest fires start inside the house. As the saying goes, if you can't stand the heat, get out of the kitchen. But Beth Weckman can't wait to get in it. Or at least into the living room.
Good.
So each of the wires on this chain is a thermocouple, and a thermocouple measures temperature.
Good.
The University of Waterloo's burn house is tricked out with new technology and old furniture. Furniture that is fuel.
And you can see now that the couch fabric is actually beginning to ignite.
Professor Weckman wants to learn more about how fire spreads in a modern house.
It's time to get out of here.
Close the door down.
Yeah.
That's why Peter McBride is here too. Ottawa Fire's Chief of Innovation and Safety.
Our furniture has a lot of synthetics. We refer to it as comfortable gasoline. And so that comfortable gasoline you're sitting on, those are all produced by oil-based products. It's very similar to someone actually physically throwing a can of gasoline on a campfire. It's really important to understand why today's fire is so much more dangerous than in the past.
Dangerous and different. They're running today's test with all the windows and doors closed, just like the energy-efficient houses so many North Americans live in.
When a fire runs out of oxygen, it's called underventilating. And if it stays in that state for a period of time and then the firefighters allow air into that environment, the fire can take off very, very quickly, and it's extremely dangerous to them.
4 minutes. That's all it takes for the couch to be fully engulfed in flames. It's called flashover.
Today, our houses have become like easy bake ovens. They're airtight for energy efficiency. And so what happens is that as that energy is held into that box and we open a door, bang, it lights up.
Well, we've just had failure.
Fire grows extremely quickly, and as you saw in this instance, it came across the couch at a high rate.
In the past, it would take about 17.5 minutes when the smoke detector went off to that room to be fully involved in flame. Modern fire, the smoke detector goes off. It can be in flame within 4 to 4.5 minutes, as low as 3.5 minutes. So you really only have a small window to get out of your house.
Airtight houses, toxic furniture. As our homes have changed, urban firefighters have had to change tactics.
So in the past, we used to think ventilation, that was breaking glass or opening doors, equaled cooling. You would break glass to allow the smoke to escape, so you would lift the smoke layer and be able to see the fire. Modern science tells us otherwise.
All right, let's go.
Now, McBride wants to put science at the forefront of firefighter training.
All right, so we're gonna let the fire progress now, okay?
You can catch that thermal imaging, shows you where the hot layer is developing.
Little bit of water, there we go.
And so they're teaching people how to manage that smoke layer.
Okay, hit the back a bit.
He's developing a new curriculum with partners that include several Canadian fire services, U.S. Homeland Security, and 13 NATO countries. Trying to spark change by making sure firefighters understand the basics.
Brad has opened up the side compartment as if we would open a window in the past, and you can see the exponential growth in that fire. It just needed air.
So smoke is the result of incomplete combustion, but it's full of all kinds of remaining fuels that haven't been able to combine with oxygen or with enough heat to ignite. So the smoke that we encounter in a building is actually fuel ready to light up.
To demonstrate how dangerous that can be, they introduce a mix of propane and air into a burn box.
Here we go. What we're gonna do here is simulate a backdraft. So what we're doing is we're getting a hot, fuel-rich, smoky environment inside of a closed compartment. We're gonna see what happens when you open a door. It's be very dangerous for firefighters if it isn't controlled.
Firefighters have to understand that smoke is fuel. Flames are what was, smoke is what will be. The potential energy is what's going to get you.
You guys ready? Yep. Right. Nice and light.
Back in Waterloo, it's time to put the fire out.
Give a shot to the ceiling.
But first, they want to cool the smoke using finesse instead of force.
Basically, our objective is to put the wet stuff on the red stuff. They're introducing small droplets of water into the smoke layer, and that reduces the flammability of that smoke. The water is almost magical. The smoke actually lifts above the firefighters. It's counterintuitive to the North American Fire Service. In the past, we would have opened up a building, give it lots of air, and then we would have hit it with very large streams of water.
Engineers are also developing new weapons like the pyro lance, which can penetrate walls by spraying granite.
The firefighters are advancing the pyro lance, which is a high-pressure jet of water and granular. It goes right through the steel plate, the cement board. Once it tunnels through, at first you'll see a splashback, and then they can release the trigger for the granite, and they're just introducing a fine water mist into the compartment. It'll go through an inch of steel in no time at all.
For scientists, when the fire is out, their job is just beginning.
So the fire is done now, and we can look at what remains, and we can learn a lot about what actually happened. So on the main wall behind the sofa that was burned out, you can see the classic V pattern that a fire investigator would look at to determine the source of an initial fire.
For some researchers, the clues to how fire spreads aren't in the ashes. They're in the sky. It's taken years for Josh Johnston to prepare for this moment. A test flight in Ontario's far north. If it works, it could change the way we look at fire.
Wildfires are very rarely left untouched. So what we're doing here is we're flying into a fire that is so remote that nobody is putting any suppression on it, and it's behaving naturally.
Johnston is a Canadian Forest Service fire analyst. He's teamed up with the National Research Council to equip a Twin Otter with cutting-edge technology.
This Twin Otter is not like any of the ones you'll ever fly normally.
2 remote sensing infrared cameras are mounted to capture the fire below. One in the nose of the plane, the other in its belly. These high-resolution cameras can see through clouds and smoke.
What we're doing here is collecting some very unique data. So what we want to do is come down low. We want to do a track around, right? Okay.
When he was a firefighter in the bush, he used to hang out of helicopters looking for hot spots. But now the cameras are doing it for him, measuring the energy released by the fire and instantly transmitting crucial information.
It's going to go straight to the guys on the ground. That's where my heart's at. Once the science progresses just a little bit further, it's going to give them precise information about which parts of that flame front could be actioned by a water bomber, which parts of that flame front could be actioned by ground crews, and how long is it going to take to get to a community? And when it does get there, is there any hope?
Out the window, it's just a wall of white. But Josh can read the smoke signals.
We were just flying over a burn scar from last year. That's too quick to have fires coming back. Once we have too many fires on the landscape, all these helicopters and tankers and crews and hundreds of people out in the bush fighting these fires, it won't work. When that happens, throwing more resources at it doesn't solve the problem. What you have to do is let fire be fire. We are in Iron Bridge, Northern Ontario, out at my family's camp here. The traditional way of actually maintaining fields around here has always been to burn them. And we're fairly low-tech folk out here, and it's actually the best way for us to keep our fields healthy.
For Josh Johnston, setting the field on fire is something of a family tradition.
That's about as wide as we're looking to go on the black edge, so go ahead. Yeah, we are definitely a family of pyros. You could say it's in our blood.
His parents and siblings have all worked for the fire service.
It looks like it's going good. We'll just let it keep cleaning up a nice break for us.
And his wife, Lynn, is a fire scientist.
The fire's going.
Yeah, the fire's going.
You got your boot on fire, Dad. My father has always insisted you can't put out a fire until you know how to build one. Anytime you want to light any sort of deliberate fire, the most important thing is making sure that it doesn't go where you don't want it to go. We didn't want the fire to make it all the way up to the camp, so we made a gate out of fire. Isn't that cool? So a control line is basically just an area where we've removed all the vegetation, the stuff that could carry a fire. So when we light a bigger fire, it'll hit this, but it won't have anything to burn. So what we're doing is we're kind of clipping its wings.
It doesn't take long for the burn to take flight.
It wants more than you're going to give it. If you give it an inch, it's going to take a mile. And so it's very much like a toddler. You got to keep it in check. As a former firefighter and a current scientist, you cannot do this job without having a healthy fear of what you're studying. And that fear comes in the form of respect. It was on this landscape before we were, and part of how we're going to make it behave and how we're going to deal with the changing climate and the changing fire activity is letting fire do what it wants to do. Because fire is changing, and when it gets worse, we need to be ready for what's coming next.
But the urge to put out this force of nature means we suppress almost every fire, including those which don't pose a risk, allowing for a dangerous buildup of fuels on the ground and infernos in the future.
Are we the victims of our own success? We want to live in the woods, but we don't want fire. But the reality is we have to change some of our behavior.
One of the solutions may lie in an ancient culture on the other side of the world. Fire ecologist Dean Yabarbuk is making a promise to his ancestors.
We all believe that spiritual ancestors are watching over our shoulder.
In this vast remote region of Australia's Northern Territories, it looks as if time has stood still. But much has changed. The Indigenous people who once lived here moved away, depriving this landscape of the very people who looked after it by fighting fire with fire.
Fire is one of the tools that we have used for hundreds of thousands of years.
Traditional knowledge is very powerful.
Setting small fires to avoid larger ones is part of that tradition. It prevents dangerously dry fuels from accumulating. Left alone, they can feed megafires.
One of the oldest living cultures in the world has shown us that it's a controllable force of nature if you nurture fire in the right way. If you ignore it, it'll always come back to haunt you.
After decades of uncontrollable bushfires charring the landscape, Indigenous fire rangers have returned to rekindle an ancient practice.
What's happening up here, this is a little bit of a patch burning.
Patch burning creates a mosaic pattern, kind of like a scorched quilt, blanketing select areas with small burns, removing grasses and leaves while maintaining the tree canopy.
We're trying to replicate that same mosaic fire pattern that traditional people have used for hundreds of thousands of years.
The rangers follow the seasons and the sun, burning early in the dry season, in the morning or at dusk, when the sun is weaker and the fires easier to control.
We are the boss of the fire. We don't want to see the fire to become a boss for us.
After I almost burnt down my mum and dad's farm when I was 6, I was terrified of fire for a very long time. I came up here and people taught me the right way to look at fire.
Yeah, a couple of really big wind and it just burnt for like a week.
Dean and Jake are part of an ambitious project that has created a blueprint for fire management.
That's shown up as a fire scar, all that light green.
One that is being replicated across northern Australia and studied around the world.
Okay, so fire scars.
Our project at first had a lot of people sceptical, and it's taken us longer than it should have to realise that we should use fire in a similar way to people that were here before us.
Once they used fire sticks. Now they use diesel torches. But the science is the same. Fire is bringing life back to the biodiversity it once destroyed.
This will have new grasses coming back, plus the animals like little wallabies and bandicoot and all that. They'll come on the feed on the burnt ground, just like you and me having a bread and toast. Well, animals like burnt toast, grass.
For the people of the rock, as they call themselves, it's not just about preserving nature, but culture.
Rock arts, those images, it's like a library for our children.
These rock paintings could be tens of thousands of years old.
That's a man.
But wildfires and the resulting smoke can damage them.
This is what it does. The black squash up here, you see this from the fire, and it's right underneath as well.
The rangers hope their small fire breaks can safeguard history. But they're also using modern technology to burn on a much larger scale.
Sentry operations underway.
This firebombing tool operates like a machine gun, releasing small capsules that create a chemical reaction.
We're putting both science and the knowledge together and see if we can work side by side to help and create a new climate change.
They are impacting climate change in a dramatic and innovative way.
Very hot, intense fires which emit more carbon by burning larger fuels have pretty much disappeared. So less CO2 being emitted into the atmosphere with large megafires.
The carbon footprint here is measurable. Satellite data shows that greenhouse gas emissions have been reduced by at least 100,000 tons a year.
Marrying ancient knowledge and modern technology is definitely the step in the right direction to managing the health of our planet.
Fire is a symbol. It's everything to us. We want to celebrate tonight is ritual practice of bringing young people and old people together.
In this ancient ritual, Dean has been chosen by elders to wear a traditional mask.
This dance hasn't been done for almost 70 or 80 years.
The dancing flames are just a natural part of the cycle of life.
Fire to us is a healer of our country. And fire is not a fear. We picked up this ancient knowledge again, and we want to teach our children, for them and for their children and their children and their children.